Let's look now at some of the data that we might have available to us and how we can use Hess's law plus available data to calculate heats of reaction. We're going to begin by looking at formation reactions. Formation reaction is how the compound would be formed from its atomic constituents as they normally appear in nature. So water could be made from hydrogen and oxygen. Both of those are gases when we have them at room temperature and pressure. But the actual value for this formation reaction is going to depend on whether or not I'm making liquid water or vapor water, because those are both possible phases for water at 25 degrees C, 1 atmosphere. Now the good news is heat of formation data is fairly readily available. In the appendix, you've got for everything in that table, you have heats of formation, and frequently other data sources will have good tables also. Now, one of the most biggest warnings I want to make is that you want to be sure to select the correct phase. It makes a difference whether you're making a liquid or a vapor. Now, if you do this, you can apply Hess's law to these heats of formation, and I'm going to leave this as an exercise or read the book on exactly how this works out, but all of those constituent atomic species are going to be the same for all of our products, so they're going to cancel out from one side of the reaction to the other. Therefore, I can use Hess's law to calculate heat of reaction by using standard heat of formation data by taking all of my products times their stoichiometric coefficients minus all of my reactants times those stoichiometric coefficients. So let's next look at an example. In this example, we want to calculate the heat of reaction for 4 ammonia gas molecules reacting with 5 oxygen gas molecules to make 4 NO gas molecules and 6 water vapor molecules. So I'm going to need data. So I'm going to go to the appendix and look up enthalpy of formation for each of these compounds. So we just calculated that for this reaction, the heat of reaction is negative 904.74 kilojoules per mole. So what does the mole mean here? It means whatever would have a coefficient of 1 in the reaction. Nothing in particular has a stoichiometric coefficient of 1, so that may feel a little confusing. But let's work through an example to see if we can make sense of this. So if I wanted to know what's the enthalpy change that would happen if I had 5 moles of O2 at 25 degrees C in 1 atmosphere that reacts completely with excess NH3. In other words, I'm going to use up all the O2 and there's always going to be NH3 there for it. So in this case it would be 4 moles of NH3. So I start with my 5 moles of O2. Then I'm going to multiply by the heat of reaction, negative 904.74 kilojoules per mole of reaction. Now, this is a mole of O2 compared to a mole of reaction. So I use a stoichiometric ratio from the reaction the way I've written it. 1 mole in the reaction corresponds with 5 moles of oxygen, meaning that I'm going to have negative 904.74, written with less ridiculous sig figs, kilojoules for this reaction. So let's find the enthalpy change if 5 moles of ammonia reacted with excess oxygen, enough oxygen so that it could be completely used. So delta H is going to be 5 moles of ammonia times negative 904.74 kilojoules per mole of reaction. In this case, 1 mole of reaction requires 4 moles of NH3. So moles of reaction cancel, moles of NH3 cancel. I'm left with just kilojoules, and the answer is negative 1,131 kilojoules for this reaction to go to completion. So what happens if you wanted to rewrite the reaction to get a coefficient of 1 for NH3? Well, I started with 4 NH3 plus 5 oxygen goes to 4 NO plus 6 H2O. In this particular case, I'm going to divide everything by 4, meaning I have NH3 plus 1 1/4 oxygen molecules makes NO plus 1 1/2 water molecules. Now, people frequently don't like this because it's hard to picture 1 1/4 oxygen molecules, but this does make it a little bit more transparent what you're doing. So what happens for heat of reaction for this case? In this case, the heat of reaction, I have 1 NO, I have 1 1/2 waters, I have 1 NH3, and 1 1/4 oxygens. And so my heat of reaction is negative 226.17 kilojoules per mole of reaction. So delta HR changes when I change the way that the reaction is written. However, my answers would be exactly the same, because to use this to solve this problem, I would have delta H is going to be 5 moles of NH3, negative 226.17 kilojoules per mole of reaction. And in this case, 1 mole of reaction is the same as 1 mole of NH3. And I end up with the same answer. In our next lesson, we're going to be looking at how heat of combustion can be used to do similar calculations.